welcome to the Deep Dive. Today we're focusing on one of the most exciting and, frankly, challenging areas in AI.
We're talking about building robots that can take what they see and hear, language and vision, and turn that into physical action in the real world.
This is the realm of vision language action models, or VLAs.
And these VLAs, they're built on the shoulders of giants. They inherit this huge amount of world knowledge from pre-trained vision language models, the VLMs.
The thinking seems so simple, right?
Mhm.
If a VLM already knows what a spoon is and what a bowl is, then a robot should be able to learn how to pick up the spoon pretty easily.
It should be a seamless transfer of common sense.
But that's where the research we're looking at finds a huge failure point. It turns out when you take these incredibly smart VLMs and try to fine-tune them for action, that deep, general understanding of the world starts to just crumble. It's kind of catastrophic forgetting.
We saw really clear evidence that this specialized training for an action, it causes the model to systematically just discard its general knowledge.
So it's like it's blinding itself.
It is. It trades that inherited visual intelligence just for the ability to grasp something.
So our mission today is to break down how this happens. What is the pathology here? And then we'll get into a surprisingly simple solution called visual representation alignment.
And look at the proof that it can actually restore what was lost.
So to understand the problem, we need to look inside the model, right? See how its internal state changes.
Yep. And the researchers found three really distinct ways that these representations collapse.
Okay, let's start with the first one. Representation collapse. They used a TSNE analysis, which, for anyone who hasn't looked at one recently, what does that show us?
You can think of it as a map of concepts inside the model's memory. A good VLM, like prismatic VLM, it has clear separation between different ideas.
Like different continents on a map.
A good way to put it. So if you map out the embeddings for, say, a cup, a bottle, and a knife, the VLM shows three tight, separate clusters. It knows the difference.
And what happened with the VLA, the open VLA model, after it was fine-tuned to do simple pick-and-place tasks?
The whole map just compressed. Those clear clusters for cup, bottle, and knife, they blurred together. They started overlapping in a big way.
So the supervised fine-tuning basically just crams all these different ideas into one tiny corner of the map that's only useful for the one task.
It loses that fine-grained ability to tell things apart. It might still be able to grab a cylinder-shaped object, but whether that's a cup or a bottle semantically, that understanding is seriously damaged.
It's giving up its taxonomy for what you could call muscle memory. So if the internal concept map is collapsing, what about its actual visual focus? That brings us to the second problem, attention sink.
This one is all about visual grounding. A pre-trained VLM is great at looking exactly where it needs to. If you tell it, find the red plate, its attention map, its gaze is locked right onto that plate.
But the fine-tuned VLA, it loses that focus. It becomes an attention sink.
It does, under what they call out-of-distribution conditions, so scenarios it hasn't seen in training. Its attention maps get all noisy and diffuse, sometimes just plain wrong.
So it's not looking at the right thing anymore.
Right. It's like a searchlight that suddenly turns into a broken floodlight. It just washes out the whole scene instead of highlighting the target.
And the researchers even found where in the model this breakdown is happening, didn't they?
They did. This failure of grounding was most obvious in the middle transformer layers. That's typically where vision and language get fused together to create meaning. The whole adaptation process just destabilizes that critical zone.
That leads us right to the third issue, domain-specific forgetting. This sounds like it's not just getting confused about similar objects, but it's actively throwing out whole chunks of knowledge.
To test this, they used a diagnostic suite called VLThink. It's based on the simpler benchmark, which uses a Widow X-arm for a simple pick-and-place task. The physical part is easy, so it really isolates the model's language and vision skills.
It's a test of its symbolic ABCs, so to speak.
And the OpenVLA 7B model showed just huge measurable drops in that knowledge compared to its base VLM.
What kind of knowledge did it forget?
The biggest drops were in abstract and symbolic categories. Things that are all over the VLM's original training data, but missing from the robotics data. We're talking about traffic signs, arrows, public info symbols, weather icons.
So if the robot is only trained to grab stuff in a kitchen, it decides that knowing the difference between a stop sign and a yield sign is just, useless data taking up space.
That's a perfect analogy. The only real exception was the color domain. It held on to its ability to sort objects by color.
Because that was still useful for the task.
It was. It suggests that only the knowledge that's immediately and directly useful for control survives. Everything else, all that general inherited intelligence, just gets pruned away.
Okay, so the problem is clear. Naive fine-tuning is destructive. This brings us to the recovery plan, which is based on this really interesting idea called the Platonic representation hypothesis.
The hypothesis is that all these big, high-performing models, whether they're for vision or language, they all start to converge towards a kind of shared ideal representation space.
A Platonic space.
A space that encodes the true general structure of what things are. What makes a chair, no matter what it is like.
And the goal then is to stop the VLA model from drifting away from that ideal space while it's being fine-tuned.
That's the core idea. And the solution is called visual representation alignment. It's actually quite a simple method. They just add a lightweight regularization term, L-align, to the loss function.
Can you walk us through how that term actually works? How does it tether the VLA back to that Platonic space?
Well, it works by anchoring the VLA's internal features, especially those unstable middle layer ones we talked about, to the features from a strong, frozen, pre-trained vision teacher model.
A teacher.
A teacher, like C-Radio V3, that acts as a stable reference point. It already has that general semantic consistency locked in.
So the VLA is learning two things at once. It's trying to get the action right, but it's also being penalized if its internal vision drifts too far from what the teacher model sees.
That's it. And crucially, the teacher model itself doesn't change. It's a stable beacon. It guides the VLA's adaptation without moving, and that's what prevents the representational collapse.
So let's get to the results. Did this simple alignment strategy actually work? Did it fix the damage?
The evidence was pretty overwhelming. On the benchmark that tests generalization, the alignment method consistently cut down on that degradation we saw. They reported up to a 10% relative gain over the naive fine-tuning.
10% is a huge deal in robotics. It means the robot is just that much more reliable when it sees something new.
It is. It's a major step towards robustness.
Now, you might think the easiest fix would be to just freeze the visual part of the VLA completely. Did they try that?
They did, and the result was very telling. Near zero performance.
Wow.
It confirms that the VLA has to adapt its visual side to work with the new action components. If you just lock it, there's a total mismatch, and the control fails completely, so it has to adapt, but responsively.
I think the most compelling proof, for me, came from the linear probing analysis, where they tested the model's features on something totally unrelated, classifying ImageNet photos.
Right. This test really measures how cleanly the model encodes semantic categories. The naive SFT model, the one with degraded features, scored about 77.5% accuracy.
Okay.
The original pre-trained model was a bit better, at almost 80%.
So the VLA starts out smart, gets dumber during tuning. What about the one with alignment?
The open VLA with alignment hit 82.13% accuracy. This is a critical finding. The alignment didn't just stop the degradation, it actively strengthened the features so much that they were better than the original foundation models.
So the right kind of training can actually refine the inherited knowledge.
It can lead to greater semantic consistency overall.
What about that domain-specific forgetting? The traffic signs and arrows, did it remember those?
It partially mitigated the forgetting. It showed definite improvements in categories like color and shape. It didn't instantly restore all of that highly abstract knowledge, but it stopped the total erosion.
Okay, so to make this practical, we need to look at the design choices. The ablation studies dug into what makes this work. For instance, where in the model do you actually align the features?
This was a key finding. Aligning the early layers didn't do much. Aligning the final layers wasn't great either. The biggest gains came from aligning the middle transformer layers around layer 16.
Which supports the theory that the damage happens in that mid to late fusion zone.
It does. It's where the visual semantics are clashing with the new action goal.
And the choice of teacher model, the Platonic anchor, does that matter? Can you use any VLM?
Oh, it matters a lot. C-Radio V3, which is a very strong generalist vision model, gave the best results. It just reinforces the idea that you need to align to a stronger, more capable teacher to get a good result.
They also used a projector, which is like a translation layer, to map the features. What did they find about the state of that projector?
The best setup used a frozen MLP projector. This was interesting because if they allowed the projector to be trainable, the model found a shortcut. It would just change the projector to minimize the loss instead of fixing its own internal states.
It cheated.
In a sense, freezing the projector forced the model to actually correct itself, which is what you want.
And finally, the loss function. What worked best to keep things stable without getting in the way of the main task?
Cosine similarity loss was the most stable, especially with a really small weight coefficient lambda equals 0.2. It was just enough of a nudge to prevent that drift without overpowering the main action objective.
So to sum up our deep dive, we've seen that when you specialize these vision language action models for a physical task, there's a steep, measurable cost. Representation collapse, domain-specific forgetting.
But this research shows a clear path forward. Using the simple, efficient visual representation alignment anchoring the VLA's internal state to a stable vision teacher at just the right spot, we can recover and even improve the visual semantics that are so critical for generalization.
The successful building of these VLAs really seems to hinge on finding this exact balance. And that leads us to a final thought for anyone working in this space. How fine is that line between specialization and robustness? How much can a model specialize for one task before it sacrifices the general knowledge it needs to handle anything new? The stability of that general knowledge seems to be the key to unlocking true performance in the physical world.